All right, we're going to continue on with our second video for section 3.1. We're still talking about graphing systems of equations or solving them by graphing them. And in this case, we're just going to be, or in this video, we're going to be looking at some examples. We're going to go over example 3, 4, 5, and then come back to example 2. So for example 3, we're going to be looking at a situation where you have intersecting lines. So in this case, our prompt is to graph the system of equations and describe it as consistent and independent, consistent and dependent, or inconsistent. And again, we went over those classifications in the last video. So here is our system. Again, we have two equations. Each one has the variables x and y. So that is our system there. If we want to solve it by graphing, if we're going to graph these two equations, we want it into slope-intercept form. Now, I'm not going to go through all the steps, but I'll write at the bottom here what the steps for each equation are to get them into slope-intercept form. And if you want to write them down, that's fine. If you feel like you remember how to solve them or move them into slope-intercept form, that's all right too. For our first one, if we're looking at x plus 1/2 y equals 5, and we want to get it into a y equals mx plus b form, we have to subtract x from both sides. And then because we have 1/2 y on the left side, we'd have to multiply everything by 2. Okay, so we get y alone. So our slope-intercept form is going to be y equals negative 2x plus 10. For our second equation, we have 3y minus 2x equals 6. Again, the first step would be add 2x to both sides. So we move our x term to the right. Now we still have 3y on the left, and we want y alone, so we'd have to divide everything by 3. When we divide everything by 3 at the end, it becomes y equals 2/3 x plus 2. Now, using these two equations, again, we still have the first equation and the second equation. They mean the same thing as the other equations. We just change them to a different, more usable form. Okay? So in our first one, if we have y equals negative 2x plus 10, that means our y-intercept is way up here at 10. It was a little bit off the chart. The slope, being negative 2, means that we come over and go down 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1. And sorry, I apologize, the smartboard's a little bit off. But that would be the slope, that would be our line there in that case. Same thing with our second equation, y equals 2/3 x plus 2. So we go to positive 2, that would be our y-intercept. And with our slope, we know we're going up 2 over 3, up 2 over 3, up 2 over 3. Go like that. So we can see how these lines kind of plot out. Now, again, they labeled each line as the original equation. So this one they labeled as 3y minus 2x equals 6. And it means the same thing as y equals 2/3 x plus 2. This one they labeled as x plus 1/2 y equals 5. And again, it means the same thing as y equals negative 2x plus 10. Now that we've graphed out our line, we can see then, again, as we follow the lines, they'll intersect right here at the point 3, 4. So at that point, our x is 3, our y is 4. So we can check just to be sure that that fits into both of our equations. If we have x is 3 and y is 4, in our first equation, we'd be saying 3 plus 1/2 of 4 equals 5. Well, half of 4 is 2, so 3 plus 2 is indeed 5. So our first one checks out. Same thing. We have 3y minus 2x equals 6, where 3 is x and 4 is y. So we'd be saying 3 times 4 minus 2 times 3 equals 6. Well, 3 times 4 is 12 minus 2 times 3 is 6, so 12 minus 6 is in fact 6. So 3, 4 is the only point that makes both of those equations true at the same time. It's our solution. Oh, before I go on, again, because we know that they intersected at one spot and one spot only, we would call it a consistent and independent system. Okay? Consistent because it has a solution. Independent because they are different lines. They're independent of each other. Now in this case, we'll have the same line. So again, kind of the spoiler alert, it tells you right away what's going to happen. So our prompt is we need to graph the system of equations and describe it as consistent and independent, consistent and dependent, or inconsistent. Now again, they give us our system right here. We have two different equations. Each one has an x and a y. And our job, again, if we want to graph them, we want to get it into a y equals mx plus b form. So in our first equation, the 9x minus 6y equals 24, if we're working towards getting y alone, the steps we'd need to do are subtract 9x from both sides. Then we'd have that negative 6y left, so we'd have to divide by negative 6 on both sides. When we do that, we do all those steps to our top equation, it's going to become y equals 2/3 x minus 4. So that would be our slope-intercept form. That one will be a lot easier to graph than 9x minus 6y equals 24. All right, same thing looking at our second equation. We have 6x minus 4y equals 16. Well, to get y all alone, we'd subtract 6x from both sides. Okay. After that, we still have that negative 4y being on the left side, so we need to divide by negative 4 from both sides. When we do that, our equation becomes y equals 3/2 x minus 4. Now again, we could graph them out, and I guess they did over here, but we can see that makes the exact same equation. So we had two different equations before being part of our system. Now it's the exact same equation when we made it, when we kind of moved things around, made it easier to graph. So it's a lot easier to see that in both cases. We would go down 4, that's going to be our y-intercept, and we go up 3 over 2, up 3 over 2, and so on to make our line. Now again, when we do that, we'd say that that plot or that line is actually going to be graphing both of our equations. Okay? Again, you'll notice both of our equations are labeled as this line. So it means they're the same exact thing. So since the equations are equivalent, their graphs make the same line. Any ordered pair representing a point on that line will satisfy both equations. So if I gave you a point on the line somewhere, it would make both equations be true. So technically, there are infinitely many spots where they overlap. So there are infinitely many solutions. We call this system consistent and dependent. And it helps me to remember them dependent because they lean on each other. They depend on each other. It's the same exact line. They need one another in that case. So independent, they're different from each other. Dependent, they're the exact same. All right, again, spoiler alert, this one's going to be parallel lines. So we are given our system of equations. We have 3x plus 4y equals 12 and 6x plus 8y equals negative 16. Okay, I'm going to fly through this because I think we kind of, we've gotten into the habit. We know what's going to happen here. If I need to solve that first equation, put it into y equals mx plus b form, subtract 3x from both sides, and then I divide by 4 to get rid of that 4 in front of the y. That's going to turn it into y equals negative 3/4 x plus 3. Okay, so that would be our first equation. The second one, 6x plus 8y equals negative 16. Well, again, moving that into a slope-intercept form, I would subtract 6x from both sides. Then, because we have the 8y, I would divide by 8. When I do that, it becomes y equals negative 3/4 x minus 2. So again, nice and easy to graph these. If we look, though, we can see right away both of these have a slope of negative 3/4. Okay, so again, you can go ahead and graph it if you want. We have our two y-intercepts. Both of them will go down 3 over 4, down 3 over 4, and make those lines. We connect them as we go. As you do, you'll notice those will never intersect. Those ones are going to be parallel lines. Okay, so there's no spot that's going to be the same for both of these lines. There's no x and y value that would make both of these equations true. So we would say, again, there are no solutions to this system. This system is what's called inconsistent. It will never overlap at all whatsoever. All right, example 2, coming back to the beginning here. Example 2 is actually kind of more of a real-life situation of how or why we can use these linear graphing or the system of linear equations to find something or to show something. So this is called a break-even point analysis. In this case, it's something that you might use in like an economics course or any time with business. So in this case, we have the story that Travis and his band are planning to record their first CD. Congrats, Travis. I'm sure you guys don't suck. The initial startup cost is going to be $1,500, and each CD will cost $4 to produce. They plan to sell their CDs for $10 each. Again, $10. I hope that band doesn't suck. How many CDs must the band sell before they make a profit? So again, it's going to cost them to make these CDs. It costs them up front just to kind of start all of this process, but they can sell their CDs for more than they're spending on each CD. So after a while, they hope to make some money off of it. Well, how much do they have to sell to actually make money? We can figure that out by just setting up two linear graphs or linear equations. In the first one, we're going to look at their overall cost. So in both cases, we'll let x be the number of CDs and y be the number of dollars that are being discussed here. So the cost of x amount of CDs. We don't know how many CDs we have, but we're talking about the cost. That's going to be our y value. So y is, or y equals, so the cost of so many CDs is, we have the cost per CD plus our startup cost. Well, our cost per CD times the number of CDs would be 4x, because it was $4 to produce each one, plus the startup cost of $1,500. So what it costs them to produce these CDs would be y equals 4x plus 1,500. So that's a pretty big graph. It's going to start pretty high up and kind of go up 4 over 1, up 4 over 1 as it kind of progresses. Well, that's fine. We can deal with that. In our other one, we're going to look at their income. So how much money are they making? So again, their income, we're talking about how much money they're making. So the income is our y. The income is, so that's where our equals come from. The income from the CDs is the price per CD times the number of CDs that they sell. So the price was 10 times the number of CDs, x. Oops. So we have our two graphs, or our two equations, y equals 4x plus 1,500, and y equals 10x. Now again, we can graph them out or plot the lines out on a graph and find where is it that these are going to intersect. Well, they intersect right here at 250, 2,500. What that means, or what that's telling Travis and his band, is that right at the time that they sell 250 CDs, that means they've spent as much money as they've made. So they have no profit there. Anytime before that, so if they sell only like 200 CDs, that would be here and here. Well, this line down here, this is their profits, or how much money they're making, should I say, their income or their revenue. The top line up here, this is their cost. Up here, their cost is more than their revenue or their income, which means they're losing money anywhere before 250 CDs. Anytime after selling 250 CDs, they're actually making a profit. So hopefully they can sell a lot. Hopefully they, again, aren't a terrible band and they'll make it. But yeah, again, that's just an example of how we can use our linear graphing here to solve for the solution to that system.